Welcome back, everyone. I would like to review what we covered in the first part of Activity 4.2a, and then we will move on to the second part of 4.2a. So, the first thing we did is we looked at the difference between different types of studies. And what we really focused our attention on were the observational study and the experiment. The observational study simply observes subjects, and the experiment imposes treatments on subjects. The next thing we did is we took a look at how uncontrolled variables can lead to confounding. So as an example, we looked at the relationship between eating an apple a day and visiting a doctor. The eating the apple a day was the explanatory variable, and visiting the doctor was the response variable. Both of those were categorical. But as part of our discussion, we also talked about uncontrolled variables like a person's level of health and how the effects of that on whether or not somebody visits the doctor can be confounded with the effects of eating an apple a day. So ultimately, confounding occurs when we can't tell the difference between the effect of the explanatory variables that we're truly interested in and other extraneous variables. And lastly, we took a look at experimental units and subjects, explanatory variables, factors, treatments, response variables, and an experiment. And we didn't talk too much about this, but most of the time, the subjects are the experimental units. Experimental units are the smallest group to which the treatments are applied. So in our example with the eating an apple a day and visiting the doctor, we could apply the treatment, the apple, to the individual subjects in the group, in which case the subjects are the experimental units. But here's another scenario where you might want to think about where the experimental units and the subjects are not the same. Let's assume that I have several fish tanks and I have several fish in each tank, and I'm going to do an experiment with different types of fish food. And so I'm going to apply that treatment, the fish food, to the entire tank. In that case, the subject, so to speak, are the individual fish, but the experimental units are the group of fish in each tank, because the tank is the smallest unit to which we can apply the treatment, because when we sprinkle the fish food in the tank, all the fish in that tank are going to get that treatment. We talked about explanatory variables and response variables. In the apple a day experiment, the explanatory variable was the apple. The response variable was whether or not they visited the doctor. So what we're going to do now is we're going to continue on with this discussion about experiments. We're going to talk about what a completely randomized design is for an experiment and discuss why control, random assignment, replication, and comparison are all important design principles in an experiment. So this was the example that we left off with in the previous video, and it went something like this. Suppose that this year the school has enough money in the budget to compare SAT online course with the traditional classroom course. 50 students were randomly selected and have agreed to participate in an experiment comparing the two instructional methods. Discuss how you would assign students to the two groups. Well, we have to use randomness to assign subjects to the two groups, the control and the treatment group. So a real simple answer to this would be randomly assign students to the control / treatment groups, one of those two, and hopefully that random assignment would equalize the effects of all the potential confounding variables. Often, experiments are diagrammed in a way shown like this below. We start out with the subjects and how we got them. They could have been volunteers. In this case, they were randomly selected and agreed. And then we break them into two groups, a control and a treatment group, or the two treatment groups, the online course and the classroom. The classroom is what I think of as the control group. And we note that we have randomly assigned the subjects to one of the two groups, and then we compare SAT scores after they've taken the courses and the SAT. This simple experiment is called a completely randomized design. It is not that the subjects were randomly selected from the entire population. It is the completely randomized design refers to the fact that they were randomly assigned to a treatment group. G asks you to explain how random assignment helps control the effects of any possible confounding variables. This is an extremely important concept when it comes to experiments. Our goal when we run an experiment is for the various treatment groups to be identical in every way except for the differences in the treatments. Then we can say, if we notice a big enough difference in the response variable, that difference must be due to the different treatments. So, since we cannot absolutely guarantee that the various groups, treatment groups, are going to be identical in every way, we have to settle for the next best alternative. And the next best alternative is for us to randomly assign subjects to those various treatment groups. And all of those possible things that we're not interested in studying the effects of, that could be affecting the response variable, hopefully are equalized. And then if we apply the various treatments to the various groups and we see a statistically significant difference in the responses, then we can say this difference is big enough so that we don't think it's just due to chance variation between the groups. We think it's due to the actual difference in the treatments. So that is how random assignment serves to equalize all the differences in the treatment groups before we apply the treatments. Very often in the activities that Ms. Harding and I assign, you will find these sections that are referred to as check your understanding. And basically these are checkpoints along the way before you would normally leave the class for the day. In this case, before you wrap up your lesson for the day, wherever that might be, that we would like you to work through to verify that you understood what we wanted you to get out of the activity. So, in this activity, problems 3 through 9 are check your understanding problems. And what we would like you to do is we would like you to read through those and ideally provide your own written explanation for those, because a big part of the AP exam and our chapter exams is going to be the written portion. It actually counts for half of our chapter exams and half of the AP exam, and the sooner you start practicing that writing, the sooner you'll get better at it, because right off the bat it's usually pretty challenging. So what we would like you to do right now is pause the video, go to the OneNote printout for activity 4.2a, read check your understanding problems 3 through 9, try writing your own solution, and then take a look at our solutions. When you're done with that, come back to the video because I have a short discussion of 4 important concepts related to experimental design. All right, so if you have any questions on check your understanding problems 3 through 9, make sure that you ask us about those. You can do that during class time, or you can contact us in other ways. What we'd like to do now is wrap up this activity with a discussion of 4 extremely important principles of experimental design. So we're going to start out with control. We need to control sources of variation. Variables, for example, other than the factor or the explanatory variables that we are testing. So we need to make the conditions in the different treatment groups as similar as possible. What this does is it allows us to say if there is a difference in the response variable from the different groups and their different treatments, and it's big enough, statistically significant, so that it probably didn't happen by chance, then we can attribute those differences to the different treatments. Okay? There are different ways that we can actually control things. We can control some of those random variations by randomly assigning subjects to the different treatment groups and balancing them out. But we can also directly control some of those variations. So as an example, let's say that I'm going to teach using 2 different methods in preparation for the SAT, for example. And I'm going to teach one class using one method, and I'm going to teach the other class using the other method. So one of the things I should do right off the bat is I should randomly assign the various students or subjects to my 2 groups to hopefully balance out all of those things that students would bring to the table, like ability and motivation and things like that. But there are other things that randomness or random assignment can't balance out the effect of. For example, what if I taught one class in an environment that was not conducive to learning? It was hot, the lighting was poor, it was noisy. And I taught the other class in an environment that was conducive to learning. It was comfortable, it was quiet, it was well lit. Those are not extraneous factors that we would control by randomness. Those are things that we would directly control. So there are a couple of aspects of control that we need to think about when we're designing an experiment. Those that can be balanced out, so to speak, by random assignment of subjects to treatments, and those that we have to directly control. All right, randomization. We've talked about one aspect of randomization, and that is actually the second one here, and that's important. By randomly assigning subjects to various treatment groups, we hope that all the different extraneous factors that could influence the response variable in our experiment should be roughly balanced out. There's no guarantee of that, but that typically happens, especially if we have a large enough number of subjects or experimental units. The other aspect of randomization that we need to think about is the subjects that were used in the experiment. And this goes back to sampling, so to speak. If we randomly select subjects for our experiment from the population that we're interested in applying these results to, then in theory, if we come to some cause and effect conclusion with our experiment, we should be able to reasonably apply those conclusions to the entire population that we selected those subjects from, because they were randomly selected and they should be a good representation of the population. However, if we didn't randomly select those subjects and they were volunteers, then we need to be very careful, and we shouldn't automatically assume that any conclusions of our experiment apply to the population from which they came, because they might not be representative of the population itself. A fairly easy to understand example of that would be, let's say we've got the scenario where we're using an online course versus an in-person course for SAT prep. If we have students that volunteer for that, which is what we would actually have to do. We couldn't randomly select subjects from the population and force them to take these courses. But if we have students that volunteered for that, there might be some variable related to their volunteering for that that also has an impact on the outcome of that experiment. And therefore, even if we establish a cause and effect relationship, being able to say, for example, that one course worked better than the other at preparing students for the SAT, we might not be able to say that those conclusions apply to the entire population, because maybe those people that volunteered actually have some trait in common that allowed that effect to occur, and those people that didn't volunteer would not have that trait in common with them. So the best experiments the only way that we can apply conclusions in an experiment to the entire population is if the subjects were randomly selected from the population to which we want to apply those conclusions. Replication, another very important aspect of experimental design, and it basically is pretty simple. It's kind of like taking a sample. If we wanted to infer something about an entire population, we wouldn't take a sample of one. We probably wouldn't even take a sample of two and measure those two subjects and say, well, this must apply to the entire population. We would want a larger sample to be more confident in our conclusions. The same idea applies with experiments. If we were doing an experiment, we would not want to have a small number of subjects in our experiment and say, oh, we found a difference between the outcomes of these two different treatments, and therefore we've got this conclusion that should apply to the entire population. That's usually a pretty bad idea. The other aspect of that is that sometimes the experimental units and the subjects are not the same. So the same idea would apply if we were talking about my fish tank example. Maybe I've got 2 fish tanks full of fish, and I randomly assigned those fish to those 2 fish tanks, and I've got lots of subjects, but only 2 experimental units, because the experimental unit is the smallest group to which the treatment can be applied. And if I've only got 2 fish tanks full of fish and I'm going to apply one treatment to one fish tank full of fish and another treatment to another fish tank full of fish, I've only got 2 experimental units. And if I see a difference, let's say, in the growth of those fish due to those different types of food, it would be a bad idea to say that it's due to the fish food itself. And that's an example of not having adequate replication. The last aspect of experimental design that we want to talk about is comparison. If we want to avoid confounding, we need to make comparisons. And here's an example of that. Let's say that I propose that yoga helps reduce people's stress. And so I have a bunch of volunteers from a particular company, and they are in a single group that gets the yoga treatment, and I find that over time their stress is reduced. Some people might say that the yoga was the cause of reducing the stress. But what they're not thinking about is that there could be other causes. Maybe it's a job whose seasonal stress levels change, like most jobs. And maybe the yoga started when everybody was at a high level of stress, and it ended at a time when their stress was declining. If that's the case, we don't know how much the yoga affected the stress reduction and how much of the stress reduction was just due to the fact that there are other factors, like the other stress factors at work, that could be reducing stress. So a proper way to do that experiment would be to have volunteers take part in this experiment or randomly select subjects, which ethically we couldn't do, and randomly assign them to the yoga treatment group and another treatment group. And then over a period of time, look at their reductions in stress and compare their reductions in stress. Then, if we saw that the yoga group stress level went down further than the control group stress level, then we can say that the treatment of yoga helped reduce stress, and we could actually tell how much. So that's it for now with principles of experimental design. We will continue on talking about other things that we can do to refine the process of conducting an experiment and flesh out things that might, explanatory variables that might have an effect on the response variable. But we'll start that with activity 4.2b.